So the question that was asked to be done was the Master in Chemistry 17.46. So this is a titration problem of a weak base with a strong acid. So this is going to be really similar to the titration practice problems that I put up on EC Learn, except that was the opposite. That was a weak acid with a strong base. My plan is to only do part B because the rest of the parts of this problem are going to be really similar. So it'll be up to you to finish off the rest. So let's take a look at this problem, right? It says, consider the titration of 30 mils of this concentration of ammonia, and it's reacting with this concentration of a strong acid HCl. And it's asking us to calculate the pH after the following volumes of titrants have been added together. So in this case, for part B, we're combining 30 mils of the 0.050 molar ammonia with the 20 mils of our 0.025 molar HCl. So like any other question I'd start with, I'm going to just summarize everything in givens and finds. So I have my volume of ammonia, my concentrations, and I know I'm specifically trying to figure out the pH in the end. So that's my ultimate goal. So with any acid-base reactions or acid-base chemistry questions, I almost always start out by writing down what the reaction is going to look like and predicting what my products are. So usually for a problem like this, I would only write down what I have here is labeled as number 2. But I'm going to try to be really explicit as I walk you guys through this type of problem. So we know our strong acid is HCl, and we know by definition a strong acid is going to approximately 100% dissociate. So even before the HCl is added to our ammonia, when you have that solution, well, even though it's 0.025 molar HCl, it's actually already undergone a reaction with the surrounding water. So all of that HCl is effectively now hydronium and chloride. So when I add this to ammonia, well, there's my hydronium, which used to be, I guess, if you want to think of it like the HCl. So in effect, the hydronium concentration here is going to be equal to that concentration of HCl that I started with. So in the titration, I have my weak base, my strong acid, and it's going to be forming ammonium and water. So this is a net ionic equation I've written here. If we had the full, complete ionic equation, that chloride would also be included, but it's a spectator ion, so I have omitted it from this chemical reaction. So now that we have our reaction, the one that we're looking at, let's start attacking the problem. The first thing we need to figure out is actually how much stuff is reacting. So we need to figure out how many moles of ammonia do I have and how many moles of HCl or hydronium, however you want to think about it. So what I have here for ammonia on the top line, I have my 0.050 molar. I've just written that out explicitly as moles per liter. And there's my 30 mils written in terms of liters. So I started with 0.015 moles of ammonia. And I can do the same thing for the HCl or the hydronium, however you want to think about it. There's my original concentration. I used 20 mils of it. So in my titration, I have added 0.00050 moles of HCl. So those are my reactants. The next step is to figure out how much ammonia is left over after the reaction is complete, and then how much ammonium did I make, right? So the way we're going to figure this out, we got to figure out first what our limiting reagent is. So I've said I started with, and here's the amount of moles of ammonia I calculated on the last slide. The amount of moles of HCl or hydronium, right? We calculated on the last slide. I'm saying at the moment I mix them together, well, there is no ammonium because I didn't add it, and we're kind of just ignoring water, right? One of the first assumptions that we talked about in chapter 17 is if we're doing a titration with either a strong base or a strong acid, we're going to say because of that strong acid or that strong base, it's going to pull this reaction all the way to the products. And pull everything to the products. So what I see here is that hydronium, or HCl, is going to be my limiting reagent. I have less of it than the ammonia. So that's the maximum amount that can react. So when it's done, because it's being pulled all the way to the products, I have 0 moles of H3O plus left. Because 0.005 moles have reacted, I'm left with 0.0010 moles of ammonia, right? Because 0.0005 reacted. So I created 0.00050 ammonium. Technically, I created the same amount of water, but it's not affecting the problem overall. So what I know now is that after that HCl is fully done reacting with that weak base, I only have a couple things left in solution, right? Oops, sorry. A couple things left in solution. I have my, I hate when this thing gets stuck. There we go. I have ammonium, I have ammonia, and I have water, right? So now I got to figure out from this information what is going to be the pH of the solution. So I take a look at the ratio of ammonia to ammonium. So I have a good amount of ammonia, I get a good amount of ammonium. As long as neither of them is 0, you can always use the Henderson-Hasselbalch equation. If one of these is 0, you'd be dividing by 0, which doesn't exist, so you can't use the Henderson-Hasselbalch equation, and you'd have to go forward with an ice table. But we're in luck. So what we need to do now is determine the pH of the solution. Right? So there's our Henderson-Hasselbalch equation. So pH equals pKa plus the log of the concentration of the conjugate base divided by the protonated acid. So one thing this problem didn't explicitly give you was the pKa of ammonium or the pKb of ammonia. My guess is they were probably going to have you either look it up in your book or you could easily Google it. That's what I did. I literally just typed in pKb ammonia and it comes up with this number, which is the correct pKb. But I got to realize that the way we derived the Henderson-Hasselbalch equation, so if you go look at the practice problems, I forget what number it is, but I explicitly derived the Henderson-Hasselbalch equation, and it's also in the notes. But it's based off of Ka, but we're looking at a base. So what we need to do is switch it around a little bit. So there's my base, but I can solve for the pKa of ammonium by using the relationship between pKb, pKa, and pKw. So 14 minus the pKb will give me the pKa. So now I have a value for pKa of this reaction. Right? I'm going to look at my log, so I made my concentration of base over acid. So A minus is technically the conjugate base. Well, the base in this situation will be ammonia, right? So remember, this A minus is just kind of a stand-in. It does not mean that the base has to be negatively charged. It's just saying it is a base, and then we have a base here. HA is the protonated acid. Again, there's my protonated acid. So my moles of my NH3 divided by moles of my ammonium. Plug that all in, and I get a pH of 9.55, which is in tolerance of what the answer key says, which is 9.56. But that's how you want to approach these styles of problems. We're going to go through essentially always 4 steps. Figure out how many moles of reactants you have. Figure out how many, what is floating around in your solution after that strong base or strong acid has reacted. You ask yourself, how much stuff do I have? So basically, if you're below the equivalence point, or as long as you've added a little bit of something to react, you'll always have a certain amount of acid and base, so you can use the Henderson-Hasselbalch equation. If you're at the equivalence point or above, you have to use an ice table. If you want a picture of that, go into the practice problem answer key on the last page. I have a little bit of a summary of that. And then the last step is always determining the pH. Most of the time, it's plug and chug into the Henderson-Hasselbalch equation. We saw in this particular one, it was a little bit more difficult because we were looking at a base, so then we had to find out what the Ka of its conjugate acid instead. So it wasn't necessarily plug and chug, but it wasn't beyond our ability to solve for it. And that's basically summarizes all titration problems. This is probably one of the harder ones. The one that I gave as a practice problems is one of the easier ones. Hopefully this helped clarify some of the problems, but the majority of titration problems are going to be these 4 steps. The only time it really changes is if you have at the equivalence point or above. Step 4 is just an ice table. That's the only difference. All right, well, I hope that helped out. Good luck. If it doesn't, send me an email, but I will see you all tomorrow.